Okay guys, welcome back to my channel. Today we'll be looking at questions and solutions on AC circuits. We've done a video on that topic already on the channel. If you have not watched that video, please kindly go back, subscribe and watch that video. Now moving on, question number 1. As displayed on the screen, it says the power dissipated in an AC circuit with RMS current 5 amperes and voltage 10 volts and a phase angle of 60 degrees is dashed. Now, we said that the power for AC circuit can come in two forms, but this question refers to this form where we said P equals IV cos phi, where I is your current, V is your voltage, and cos phi is called your power factor. Now, from the values given in the question, we then say the power becomes equals the current was 5, the voltage was 10, and then cos 60. So we have P equals 5 times 10 gives us 50. Now what is cos 60? When you press your calculator, that will give you 1/2 or 0.5. We can cancel out those values and get our power to be 25 watts. Okay, question number 2, as displayed on the screen. It says the voltage of the domestic electric supply is represented by the equation V equals 311 sine 314.2 T. Please, that's an error. It's not 7, it's T. Now, determine the frequency of the AC supply. Now, as we said earlier on, the voltage given to us is called instantaneous voltage. Instantaneous voltage. How do I know? It depends on time. Now, the actual formula is V equals V naught sine omega T. V equals V naught sine omega T, where V naught is the peak voltage, omega is the angular frequency, and T is the time. Now, if you compare what we have together, we can observe that omega in this question becomes 314.2. So let's write it out. Omega is actually 314.2 for this domestic supply. Recall that omega is 2 pi f. We're asked to find frequency, so we can divide both sides by 2 pi. Dividing both sides by 2 pi, this takes out this. We have frequency to become 314.2 divided by 2 pi is 3.142. If you move the decimals further, you're going to have over 100 and this cancelling that. Therefore, if you press your calculator, this should give you an answer around 50 hertz. 50 hertz. Okay, question number 3. It says, in a purely inductive circuit, the current dash. In a purely inductive circuit, the current dash, option A, lags behind the voltage in phase by 90. Option B, leads the voltage in phase by 90. Option C, is in the same phase with the voltage. Option D, lead the voltage by 100. Now, in an AC circuit, you either lead or lag by 90 degrees, so 100 is out of it. Our answer lies between option A and option B. Now, let's see what happens here. For a purely inductive circuit, I'll give you a shortcut I know. When it's talking about purely capacitive circuit, for purely capacitive circuit, current leads voltage by 90. For purely capacitive, C for current. Therefore, for purely inductive, the reverse becomes the case. Therefore, in purely inductive, current will lag. Now, if current should lag, that means the voltage is leading. So which option in that case is correct? Option A, the current lags behind the voltage by 90. Question number 4, as displayed on the screen, says, in the AC circuit diagram above, the resonance frequency is dash. Now recall, resonance frequency is 1/2 pi square root of LC. We've explained what resonance is in our previous video. Please go back and watch that previous video on AC circuits. Now moving on, from the parameters on the diagram, we have that the inductor has 8 millihenry. So that is 8 times 10 raised to the power minus 3. Milli is 10 minus 3. And then the capacitor value is 5 micro. That is 5 times 10 raised to the power minus 6. When you press all that in your calculator, the answer should give you 2,500 divided by pi. We left our answer in terms of pi because of the way the options were kept. So this is the answer to this question. Question number 5, as shown on the screen. It says, in the series AC circuit shown above, the PD, that's potential difference, across the inductor is 8 and that across the resistor is 6. Find the effective voltage. Remember, we said the effective or total voltage when relating to voltage across each parameters can be given as square root of VR squared plus VL minus VC all squared. VL minus VC all squared. Now, this is the voltage across the resistor, and this is the one across the capacitor. The inductor rather, sorry. This shape is for inductor. Now, there is no voltage across capacitor here. So we can say this VC automatically becomes 0 because there's no capacitor in this circuit. Now, working what we have, our total voltage becomes square root of the VR becomes 6. We have 6 squared plus VL becomes 8. We have 8 squared. And this should give you square root of 6 squared 36. That is 100. And the final answer becomes 10 volts. 10 volts. Okay guys, question number 6 as displayed on the screen. It says, at what frequency would a 10 Henry inductor have a reactance of 2000 ohms? Already I wrote out the value for the inductance, 10 Henry, and then the reactance was 2000 ohms. Now we're asked to find the frequency. Recall we said XL must be equal to 2 pi FL, where XL is the inductive reactance, F is the frequency, and L is the inductance value. So putting in our parameters, we're going to have 2000 to be equals 2 pi. We're looking for F, and then L is obviously 10. So you can cancel out the 0 with the 0 and cancel out this 2 with this 2. So we have 100 here. Therefore, dividing both sides by pi, so I'll be left with F on the right hand side, and we can see the frequency becomes 100 over pi hertz, and that becomes the answer to that question. Okay, question number 7. It says, a 2 Henry inductor has a negligible resistance and is connected to a 50 over pi hertz AC supply. The resistance of the inductor is dash. We are asked to find the inductive reactance. Remember, inductive reactance, as we earlier said, is 2 pi FL. Therefore, we can say XL becomes 2 times pi. The frequency is 50 over pi, and the L is 2. We can cancel out pi by pi. Therefore, XL becomes 2 times 2 is 4, times 50 we have 200. The answer becomes 200 ohms. Okay, question number 8, as displayed on the screen. It says, in the AC circuit, the current value is dash. So from the diagram, we have these parameters given. Obviously, this is the resistor and this is the capacitor, but we're given the capacitive reactance. So let's find the impedance first. Remember, recall the impedance becomes square root R squared plus normally XL minus XC all squared. But now in this circuit, there is no inductor, so our XL value, we can take it as 0. So I'll just XC. I'm sure you know that negative XC squared remains positive XC squared. So we can say the impedance becomes square root of R squared plus XC squared, which then becomes, the R is 30, so we have 30 squared plus 40 squared. So our Z should become, if you add those two guys together, it should give you 2500, and that gives you 50. So our impedance is 50 ohms, but we're asked to find the current. Now the total voltage in the circuit is 200. Recall, our total voltage can be current times impedance. Okay, so therefore total voltage is 200 equals current times impedance. Therefore, if our impedance is 50 here, we've solved for that, so we have 50 over here, so we can divide both sides by 50, so we can get our current. 50 cancels 50, and I'm sure you can see that the current becomes 4 amperes. 4 amperes. 4 amperes. Okay, question number 9, as displayed on the screen, it says, in the diagram above, determine the root mean square current. Now, you observe we're given the root mean square voltage, and we're given the resistor and the inductive reactance. Again, let's find the impedance. Recall, impedance becomes square root. Since I have just resistor and inductor in this circuit, we can simply say R squared plus XL squared. R squared plus XL squared. Now moving on, our impedance becomes square root. The R is 4 squared, XL is 3 squared. This should become square root of 25, and that should give us 5. So our impedance is 5 ohms. Now we can find the root mean square current, because remember, the root mean square voltage is equal to the root mean square current times the impedance. So we have this as 240. We are looking for the root mean square current, and our impedance we just got to be 5. Divide both sides by 5. This takes out this, so therefore the root mean square current becomes, can 5 go into 240? Yes, that might give you 48. We have 48 amperes. 48 amperes as our answer. Okay, question number 10 as displayed on the screen. It says a DC of 5 amperes produces the same heating effect as an AC of dash. A DC of 5 amperes produces the same heating effect as an AC of dash. Option A, 50 amperes root mean square current. B, 5 amperes peak current. C, 5 amperes root mean square current. And D, none of these. The answer to this question is option C, 5 amperes root mean square current. Remember, I told you guys that when talking about AC circuits, the root mean square value of any component in the AC circuit is equal to something we call the DC equivalent. So when you hear DC equivalent, that relates back to the root mean square value. So a current of 5 amperes in DC will be 5 amperes as root mean square for AC. That is the correct answer.